Okay, let's come back to the second part of chapter 3 for special topics of semiconductor technologies. Um, that's the section we discussed the atomic structure of single crystal silicon. So for single crystal silicon, each one of the silicon has to be bonding with another 4 atoms. So you have to bonding with another 4 atoms here. To form a covalent bonding and form a atomic structure similar to the argon. And now, suppose we have the center electron replaced by argon. And argon has 5 electrons. It's a group 5 element. So that means at the outermost SMP electron shell, it has 5 electrons. After covalent bonding with every 2 electrons with adjacent silicon atoms, you got 1 extra electron, which is not bound to each one of the electrons. So this is the electron we are interested in. Based upon the atomic structure, the band structure for silicon, we know in between the covalent bonding, valence band, and conducting band, we have electron energy gap 1.1 electron volt. After introducing the extra electron by way of the group 5 element, you came up with the new energy level here, just below to the conducting band. We call this energy level with donor level, donor energy level, ED. And this is somewhere between next lower with the energy level lower than the conducting band, about 0.05 electron volt. So it's very close to the conducting band. Comparing to the valence band and conductive band, it has 1.1 electron volt. So the electron here is very close to the conducting band. If you introduce 10 atoms, 10 arsenic atoms into the silicon, then you are creating 10 atoms at the donor level. In this case, if you have extra energy comes in either by heat, by electromagnetic radiation, the electron at donor level absorb energy, it can jump to conducting band. So once you have electron jump to conducting band and you leave behind a hole over here, you jump, you leave behind a hole, you jump, you leave behind a hole. In that case, let's look at how we define conductor. We mentioned that to be a conductor, there's 2 criteria. First, you have electron at conducting band. Or Second, you have hole at valence band. This is two criteria to define a conductor. You have hole at conducting band, the electron at conducting band, or hole at valence band. So when you have arsenic add into the silicon crystal, the extra electron occupied by donor level very close to the conducting band. When you have external energy applied, the electron absorbed energy will jump to conducting band and leave behind hole at donor level. In this case, all these electrons meet with the first criteria, electron at conducting band. So this electron can contribute in conductivity. But the hole over here, the hole at the valence band, at the donor level, it's not at the valence band. So hole at donor level do not contributing any conductivities. So if you introduce 10 atoms, 10 arsenic atoms to the silicon crystal, you can have 10 electrons jumping to conducting band. If you introduce 10,000 electrons, then you will have 10,000 electrons contributing the conductivity over here. So that means for this type of material, the conductivity can be controlled by the concentration of the donor materials, which is arsenic. In the case whether or not you will have electron jumping from valence band to conducting band, if that happens, it will form a hole and electron, the so-called electron-hole pair. And the electron at conducting band and hole at the valence band both will contributing conductivities. From the solid-state physics point of view, the electron can jump from low energy level to high energy level. It always can jump from low energy level to high energy level. It's just a matter of probability. How many chances you can jump to the higher energy level? The probability. The larger the energy band gap, the lower the possibility. Okay. Also, the lower the temperature, the lower the probability you can jump to high energy level. So that means when temperature increase, the probability for electron jumping from low energy level to high energy level form electron-hole pair will increase. But since in between with 1.1 electron volt, it's quite large energy difference between these two band level, comparing to the donor level has about 0.05 electron volt next to the conducting band. So other than the absolute 0 degree K, 0 K, all the electrons occupy at the lowest energy level. Once the temperature increases, electrons try to jump from low energy level to high energy level. How many electrons jump to the high energy level? It's just a matter of probability. When temperature increases, you always can find electron jumping from low energy level to high energy level. The higher the temperature, the more the number of electrons jump to conducting band. In the case of semiconductor, it's still very little number of electrons jumping from valence band to conducting band. So if you have introduced 10,000, if you have 10,000 electrons introduced by introducing 10,000 arsenic atom into the silicon, then you can creating 10,000 electron here. But at operating temperature, it might have jumping up from valence band to conducting band. You may have, say, 5 electrons. In that case, you have 5 plus 10,000 electrons contributing the conductivity, and another 5 holes contributing conductivity. 5 electron hole pair, and extra 10 electron by way of introducing group 5 arsenic. So the conductivity basically came from the impurity, the dopant that you introduced. You always have some minor charge carrier, which is hole, contributing the conductivity, but this can be neglected because it's so small. Basically, you don't need to worry about that. So in this case, if you have a material, the electron jumping from valence band to conducting band by itself due to the temperature increase, or maybe you have other energy applied, in that case we say this is so-called intrinsic semiconductor, the property of intrinsic semiconductor. By itself. But if you have introduced donor element into the silicon wafer, you're creating a donor level over here, and those electrons jump to the conducting band, leave behind hole, and only the electron here contributing conductivity. The hole over here does not providing conductivity here. In this case, all those conductivity come from outside, come from the control of yourself. We call this extrinsic semiconductor. Intrinsic and extrinsic semiconductor. Okay, so extrinsic semiconductor is something called doped semiconductor. Okay, for intrinsic semiconductor, electron jumping from valence band to conducting band, and you're forming electron hole pair. This will be very small number. In general, you can neglect, but keep in mind, you always have intrinsic electron hole pair. It's important in the future. And because of you introducing group 5 element, you got one extra electron. So eventually the concentration you introduced into the silicon and contributing the primary conductivity here, and which is by way of charge carrier of electron. The charge carrier of electron with negative charge. So we say this is so-called N-type semiconductor. For silicon wafer, you introduce group 5 element, you will form N-type semiconductor. The next we'll discuss the so-called P-type semiconductor. It's a similar concept. Instead of introducing group 5 element, you introduce boron. Replace the center silicon atom with boron. Boron is in group 3 element. It's a group 3 element. That means at the outermost electron shell, it only has 3 electrons. So after forming a covalent bonding with the neighboring silicon atoms, you are creating a hole because you want that electron. You are creating a hole over here, and the energy of this hole is somewhere above the valence band, about 0.05 electron volt, and this energy level we call acceptor level. Okay, alright, this is, we say this acceptor, okay, A, C, C, E, P, T. This acceptor energy level, EA. Acceptor, okay. This acceptor, not donor. Donor is for group 5 element. Okay, similar situation. If you introduce 10,000 boron atoms, you're creating 10,000 hole here. The 10,000 hole in energy gap we are not contributing any conductivity, because as we mentioned that the conductivity came from the electron at conducting band and hole at valence band, not hole at energy gap. And then when you apply external energy, electron, other than jumping from the valence band to conducting band, form electron hole pair. The electron jump from valence band to the acceptor level, leave behind a hole. Similar process. Electron jump to the acceptor level, leave behind a hole. So in this case, if you have 10,000 boron atoms introduced in the silicon, you are going to have 10,000 electrons jumping to acceptor level and leave behind 10,000 hole in valence band, and these hole in valence band contributing the conductivity. Again, you might have electron jumping from valence band to conducting band due to the intrinsic semiconductor properties. Let's again say there's 5 electron jumping to conducting band. So you're going to have 5 plus 10,000 hole as the primary charge carrier contributing the conductivity, and you got extra 5 electron at the conducting band. This is a minor charge carrier. The primary charge carrier, the conductivity is controlled by the concentration, by the number of atoms you introduce into silicon wafer. So the primary charge carrier is hole with positive charge. So we say this is so-called p-type semiconductor. When silicon doped with group 3 element boron, you form a p-type semiconductor. This slide shows you the concept of Hall movement. Hall is a conceptual concept. Electron moving from a point to the other one. Okay, electron moving from one point to the other one, and it will leave behind a hole. Next, when the electron move to another place, a hole will leave behind. It looks like the hole is moving. Okay, it looks like the hole is moving. So actually, when you electron move to a hole, so this become an electron and this become hole. They exchange position, so electron move quite similar to the hole moving. So the movement of hole is a concept like electron moving. Under an electrical field, the electron always moving from negative side to positive side under a electrical field. Okay, you have electrical field, an electron will move from the negative to the positive side, and on the opposite, so the hole will moving from positive to negative side. Based upon the observation, a conclusion is made that the electron mobility, the capability of movement of electron and hole is different. The electron has a higher mobility compared to hole. Okay, electron has a higher mobility compared to hole. So that means electron move faster than hole. Electron has a higher speed than hole under the same electrical field. So after introducing the elements, let's see. If we have a specific concentration of dopant for N-type silicon dopant, that means arsenic, then you will have a resistivity somewhere here. But for boron p-type material, this is p-type, this is n-type. So you can see at the same dopant concentration, N-type and p-type semiconductor has different resistivity. That means the lower the resistivity means higher conductivity. Okay, so for N-type material, N-type semiconductor, with the same dopant concentration, it has higher conductivity because of higher mobility, higher speed. It moves fast than p-type semiconductor. The hole and the electron, the mobility is different. The mobility of electron is greater than hole. That's why electron move faster than hole. So now you know a concept of how to control the conductivity or the resistivity, because it's a reciprocal property, reciprocal related to the conductivity. Okay, so now you have the concept here right now. You can control the resistivity by way of different dopant concentration. Actually, this is the way to build a resistor on top of a silicon wafer. By way of introducing different dopant concentration, you can control the conductivity, i.e. the resistivity. It is a resistor. Okay, that would conclude this part. This part we discuss about what is p-type semiconductor and what is n-type semiconductor, based upon the element that you introduce into silicon. For group 4 silicon substrate, if you introduce group 5 element, you have one extra electron, and that one extra electron we are creating a donor energy level just below the conducting band, very close to the conducting band. So it's much more easier to jump to the conducting band for electron moving in conducting band, contributing the conductivity. The conductivity primarily comes from the electron with negative charge particle. So it's negative charge particle, so n-type. And for p-type, you have boron, group 3 element. When you introduce boron, replace one silicon, you creating a hole because it has one less electron than silicon, and you are creating a so-called acceptor level EA, acceptor level EA, just above the valence band. So electron is much easier to jump to acceptor level and creating a hole in behind, and all these hole can contributing the conductivities, and the hole with positive charge. So we call this p-type semiconductor. Okay, and you can control the concentration of the dopant to control the resistivity, so you can control the conductivity. The higher the mobility of electron give you better conductivities when you have the same concentration of dopant. Okay, now conclude this part of the introduction of n-type and p-type semiconductor.